All right, hello and welcome everybody. This is Brandon Burton with CoreLogic and welcome to Technically Speaking. I just realized I went off of mute on the wrong button. I should be coming through now. So hello and welcome to Technically Speaking episode 7. And today we're going to talk about interstitial, beyond the visible. So with that in mind, a couple of quick housekeeping things. Remember that we don't use the chat during Technically Speaking, we use the Q&A. So make sure that you know where that Q&A icon is. So that you can drop your questions there as we go through. At the end of the session today, for everybody attending this live with us, we will go through a live Q&A session. If you're watching the recorded version later, unfortunately, you don't get the Q&A. So anybody who's watching this afterwards, just a quick note, join us live and get the Q&A. So with that, let's go ahead and roll into it and get started. My name is Brandon Burton with CoreLogic, and I am the Vice President of Technical Application and also kind of a change in title here a little bit, but I am the Senior Director of Industry Relations. So I'm also the chair of the ANSI ICRC standards and serve the industry in the capacity of overseeing the standards writing and development for the ICRC. A lot of what I share in Technically Speaking comes from that perspective, by the way, just covering off on some of the stuff that's in standards and also sometimes even talking about what's developing in standards. So as we go through today and talk about today's topic, there's a lot of standards related content. I'll make sure I kind of call out where we touch on some of those standards related topics. With that said, let's go ahead and roll forward into today's presentation. With interstitial cavities and talking about how we deal with interstitial spaces, let me first kind of give you an overview of where all will go. First, I just want to make sure that we understand what interstitial means, and we'll talk a little bit about what that means. But at a high level, what it means is that we need to understand the structure as a whole, right? We need to think beyond the visible and what we see when we walk into a space. Many times the challenges that we deal with in drawing are far beyond what we can actually see within that environment. It's the stuff that's beyond what our eyes can see that really gives us a lot of the headache and a lot of the challenges. So our ability to think of the structure as a whole is critical in developing an appropriate drying plan, whether that be the equipment that we're using, the monitoring strategies that we're going to use, the adjustments that we're going to make along the way. Really critical to think much deeper than just the surface. To get to that point, we need to understand some terms. So as with many of our Technically Speaking series, terminology to me is a really important thing in a technical industry like this. So I want to make sure we understand exactly what we mean by interstitial. We're also going to talk a little bit about accessing interstitial spaces. There are definitely some options for the way that we can get into these spaces, not only for inspection and monitoring purposes, but also for drying. So I want to touch on that topic a bit today too. And then the systems that we use. So once we have access into an interstitial space, what do we use to dry that space if it is indeed wet? And in drying that, not only understanding the different system types, but how do we monitor those systems and leverage their benefits and make sure that we're really getting out of these specialty systems what we intend to get out of them? So that kind of gives you a feel for the scope today. The biggest piece of this is just going to be understanding these interstitial spaces at large. That's the primary focus today. And then making sure that once we understand that, again, we also understand how to access them, how to dry them, how to monitor that drying system, et cetera. So with all that said, let's go ahead and start off with some key terminology. The first term here, or the single term that I really want to define, is just what do we mean by interstitial? The word interstitial is used in a lot of different industry in different ways. In the water damage mitigation space, when we say interstitial cavity or interstitial void or interstitial at large within the environment, we're talking about a space or a segment or an area that is occurring between or is an interval between two different spaces and forms its own independent space. The space by interstitial typically also means it's not occupied, it's not intended for living. This could be a wall cavity, this could be an attic, this could be a crawl space, this could be the very, very small interstitial cavity beneath the hardwood floor, behind cabinetry. These are all spaces, air pockets, if you will, that exist throughout the structure that if I were to simply place an air mover in the middle of a room and turn it on, where I'm not going to generate airflow. right? Where if I put a dehumidifier in that space and start controlling humidity, I am not going to directly control the humidity in these interstitial spaces, not unless I do something in addition to ensure that the effect of those mechanical systems is being imparted onto those interstitial spaces. And that's part of the reason why this becomes so critical, is because, you know, when we go in to dry a building, 99% of the resources that we typically deploy, if not 100% of the resources we deploy, do a great job of accessing everything that you can see, right? If my eyes can see it, then generally an air mover can impart air on it. And if an air mover can impart air on it and create circulation and velocity, then the dehumidifier in that space is also going to affect it, right? But as soon as we get into these interstitial spaces, these barriers, these restrictions, these layers and surfaces are all going to prevent all of those mechanical means from affecting those wet evaporating surfaces in that little microscopic environment or macroscopic environment. So what are the interstitial spaces we're talking about? So here's a really simple schematic of a building, right? Very, very simple, where we're showing just a couple of rooms here. On the left-hand side, it looks like we've got some sort of a carpeted space. On the right-hand side, we've got like a hardwood floor, maybe inside of a kitchen with some cabinetry. You can notice this is an above grade building. So we've got a crawl space underneath. We've got an attic area up above. And don't look at this and think it's supposed to be a technically accurate spec for a building. It's just something I drew in PowerPoint real quick. So if it's missing some structural members, don't hold it against me. But with that said, this is just a really simple schematic. And in this schematic, I just want to call out some of the very common spaces that I'm going to refer to today as being interstitial spaces. The first one here is going to be the wall cavity. So over on the very far left-hand side top, you can see that I'm calling out an exterior cavity here and kind of magnifying that a bit. You know, in between the drywall on the inside and the sheeting on the outside, and mixed in with this insulation and studs and framing, we have this air, this space that is enclosed by surfaces that may or may not be wet, that may or may not be affected. And again, the reason why this conversation is so critical is because if I put an air mover in that carpeted room on the left and a dehumidifier in that room on the left, and I start circulating warm, dry air, that's not going to do a whole lot for the wall plate at the bottom of that wall if the wall plate is wet and affected, right? It's not going to do much, if anything, for the insulation in that cavity if it's wet and affected. And it may not do much for the drywall if the drywall is wet on the back side of that drywall, or even the gypsum is wet, especially if the interior is finished with a high glossy enamel paint, right? Or there's some wall paneling or some wainscoting that has encased the interior surface of that wall. In all of those instances, the wet evaporating surface is not being exposed to my drying system. And that's the real question that you want to think through when we talk about interstitial spaces, interstitial cavities. Where is the wet evaporating surface? And if that wet evaporating surface is in this interstitial space, or there's a chance that it is, then we need to access it. We need to inspect it. If it is wet, we need to impart mechanical systems or mechanical drying system of some sort. And if we do that, then we need to monitor it, right? Anything that we're trying to dry or we're putting resources out to dry, there needs to be some data that helps us understand, are we effectively causing change? Are we affecting moisture within that environment? Just the same way that I would inside the room itself, right? In terms of monitoring humidity and monitoring moisture content, you know, all of those things now need to be a part of my scope of monitoring, if you will, so that we understand if the system is effective. So here we have a wall cavity. In addition to the wall cavity, down beneath that, we also have this large interstitial space in this particular structure that would be the substructure, the crawl space environment, which 99% of the time is also going to be affected if the flooring is affected above it. Moving over to the right-hand side of the image, it's potentially an area that has to be dealt with as an attic space, depending on where the source of water is and how it migrated through the building. Cabinetry is an interesting one because it creates lots of interstitial spaces, potentially. Cabinetry and built-ins both, where we have the area down beyond and behind the toe kick. We also have the area behind the paneling on the back side of the cabinets, which can be an entirely separate and independent affected area or interstitial cavity or space. You may even have on the back side of the cabinet at the bottom, so very, very lower right-hand corner behind the cabinets, another entirely separate interstitial cavity and void, which is behind the counter or cousin to the toe kick, right? So the framing members on the back side. So lots of interstitial cavities that can be created by cabinetry and built-ins, depending upon how they're constructed. And then you have much smaller interstitial spaces. So if you have something like a hardwood floor that has been installed over a plywood subfloor, then you're going to have an interstitial space that's going to exist between the hardwood flooring and the substrate that's down beneath it. Very commonly, that hardwood floor is going to have some sort of a fluting system, an area channel that is milled out the bottom of these boards, and that's going to create an air space that is beneath that hardwood floor. Very small interstitial space, but still an interstitial space all the same. So all of these are what we are referring to as interstitial spaces. And I'm just listing a few, right? There could be more interstitial cavities and voids from things like plenums, for example, or electrical chases, especially when you get into commercial environments and commercial built spaces. The number of and the complexity of these interstitial spaces can be substantially greater. So now that we've kind of identified what is an interstitial space or where are these interstitial spaces, I want to take you through an example of just how much interstitial space you're going to have in a mitigation project. So just kind of walk through this example with me. So let's say we have a home, and this home it's relatively small. It's 1,100 square feet in size, right? So it's got a footprint, a floor footprint, if you will, of 1,100 square feet. Most of us, when we look at how many cubic feet of airspace are inside of that structure, we use that entire footprint of 1,100 square feet, and then we multiply that out by the ceiling height, right? What is the delta between my deck height and my lid, my ceiling? If I've got an 8-foot ceiling, that's 8,800 cubic feet, right? 1,100 square feet, 8-foot ceiling, 1,100 times 8 is 8,800. So 8,800 cubic feet. Well, let's think about the interstitial spaces for a minute. All of the wall cavities in this home, if you do just common construction density in terms of how much open space versus wall space there is, in an 1,100 square foot structure, you can have about 220 linear feet of total wall space. If you calculate out the cubic footage for that, that's 950 cubic feet. So out of the 8,800 cubic feet, right off the top, 950 of those cubic feet are interstitial space, just because of the wall cavities. Now you have things like cabinets and built-ins, all right, and other types of structures that are built into that space that are also going to create interstitial cavities and voids. If you take the cabinetry and built-ins on average, you've got about another 25 cubic feet of interstitial cavities in space. So what that equates to is that of that 8,800 cubic feet, only 7,871 are going to be properly managed by your traditional dehumidification and air movement. Think about that for a second, all right? 11% of the airspace in the average small home is going to be interstitial. And if I had extensive migration of moisture that has affected the entire floor area throughout the space, then 11% of that migration, if you will, is going to be creating, or 11% of the airspace that I'm trying to manage evaporation, dehumidification, et cetera, 11% of it is going to be generally out of reach of our traditional drying equipment. That's a pretty good chunk. Now, that's just considering the livable floor space. Let's add into that the attic and the substructure, right? The attic is going to be about 1,400 cubic feet. The substructure is about another 3,300 cubic feet. In total, that gives us 13,500 cubic feet. 13,500 cubic feet. And if you consider that only 7,800 cubic feet of that was visible interior space, that means 42% of the total structure is interstitial. 42%. Now, we don't deal with attics a lot, but we do occasionally, depending on where the water comes from. And if you're in a region where we're dealing with a lot of crawl spaces, then that 3,300 cubic feet is probably going to affect you quite a bit, right? So again, the traditional install of air movement and dehumidification, that traditional install, that 99% of the equipment that we typically put in is only going to properly manage about 58% of the space, 42 from 100, right? So about 58% of the space, even though it's 99% of the equipment we're installing. Now, the reason I go down this road and I kind of walk through this example is just to really help drive home the importance of considering interstitial spaces, right? The rest of what we're going to talk today is going to fall as a moot point, right? If we don't recognize how critical this is, just based on the sheer numbers, the amount of interstitial space that we're dealing with in the average building. Okay, so know it's there, know it's part of the program, if you will. And it's something that needs to be inspected. We need to identify it, know that it's there. We need to assess whether or not water has migrated into it. If it has migrated into it, again, we need to ensure that our drying means are going to affect it. We need a plan for how we're going to monitor it and verify that those surfaces and materials are dry. Okay. So now that we've kind of set up what interstitial cavities and spaces are and the importance, let's talk a little bit about some of our options for access into these spaces. So there are a number of different ways that we can get into an interstitial cavity or a void. It depends a lot on the construction. It depends actually quite a bit on where you live and what your laws and regulations are and what your licensing is. That's going to have an impact on it. So when I talk about the options for access, there's lots of disclaimers that I have to put out about making sure that you don't kind of go beyond your area of expertise. Make sure that you have the right licensing for your area if you're going to make access into a space. Be aware of hazardous materials, be aware of electrical concerns, et cetera, et cetera, et cetera. For all of those reasons, plus the fact that we're trying to avoid demolition and repair, I've ordered these in the order of operation from least invasive and preferable access to most invasive and least preferable access, starting with the first. So the least invasive way to access most interstitial cavities and spaces is just use existing openings wherever they exist, right? And that could be fixtures, that could be, depending on what it is, it could be existing, accesses and vents. Obviously, we want to look for those first. And where those exist, a lot of the challenges in accessing an interstitial cavity or void, a lot of the challenges, not all, but a lot of the challenges are avoided. The exception to that rule would be that if you're removing electrical fixtures in order to make access, depending on where you are and where you operate, it may actually require a general contractor's license just to remove that plate and gain yourself some access. So just be aware of what your local laws and regulations are. So that would be the first option, just remove or use existing openings rather. The next, getting into trim and fixture removal. Trim generally is going to be the first option that I'm going to lean towards when I'm starting to get into cavities that don't have other types of openings that I would easily be able to access, because trim gives me a great option for covering the access that I'm about ready to make. Whether that be access for my moisture meters, that be access for a borescope and inspection purposes, or even access for my drying systems. In fact, some drying systems you can get away with not even removing the trim necessarily, just repairing the caulk line at the top of the trim when you're done with the drying system. We'll talk about that in just a moment. So trim and fixture removal will be the next layer. Drilling and boring and creating openings. Hopefully this is in combination with the trim removal that we talked about just above, but that would be the next layer of invasive access into an interstitial cavity or void. And part of what will mitigate how severe this is going to be your equipment selection. Because if we have the right specialty drying equipment, we can really minimize the openings that we create. If we don't have necessarily the best equipment for the job, we may have to make much larger openings. So there'll be a kind of a relationship between these two that we'll touch on. Then last but not least, if none of the above is going to work for me, we've got complete component removal, right? And remember what we mean by component. This comes from an earlier episode of Technically Speaking. We have assemblies, right? A wall is an assembly. And then we have components. The wall board on a wall is a component of the wall assembly, right? So we may be able to remove components. For example, if I've got wainscoting on a wall and I want to make sure I have direct access to what's behind it, maybe remove the wainscoting if that's the best option, if that's the only option, right? I would much rather remove the trim, make my access behind the trim, and then replace the trim than remove all the wainscoting. So that's, again, the reason why we order this in this list of operations. Start with your least invasive. And that's a universal rule across all of mitigation, right? Our purpose and our goal in water damage mitigation is to mitigate the damage, right? Not to cause more damage, not to cause more invasion. So we always lean towards the least invasive approach and then work up that invasive list as we need to, as the job dictates, when it's necessary. But always start with the least invasive. In fact, I'll go one step further in that and state that in some cases, even for my drying systems, I will start with the installation of a system that is less invasive even if I'm on the fence about whether or not it'll work, just to give it 24 hours and find out if that less invasive approach will be effective. And if that less invasive approach is effective, great. I just saved a significant amount of repair and restoration when we're done. If it wasn't effective, then I've got my justification for taking a step up, right? Because the less invasive approach was not effective in that first 24-hour period. So I really follow that as religiously as letter of the law. Start with your least invasive approach wherever possible, wherever practical, and then move yourself up that list of invasive techniques. And you'll be amazed, if you automatically always start with a wall assembly by drilling and boring and injecting air, and that's how you always start, and you start with a little less invasive approach first, give it 24 hours, you'll be amazed how often you can make better progress than you anticipated and avoid some of the restoration costs and repairs that you traditionally are adding and tacking on to every time you have a wet wall. So more on that in another episode. We can get deeper into invasive versus aggressive drying methods at another time. So again, just kind of a reminder on the disclaimer. I started with the disclaimers. I want to end with the disclaimers because we're talking about some safety hazards here. So again, understand and know your limitations when it comes to accessing interstitial cavities and voids. Know what your skill set is capable of. Know what safety concerns will be present. Electrical safety is one of them. The other is hazardous materials that may be present. As soon as I start disturbing assemblies, I need to understand the likelihood that something like lead or asbestos will be present. I also need to understand the laws and regulations locally, right? And understand your state requirements as it relates to the disturbing of a wall assembly, regardless of age of building, right? For example, I live in Washington State, and in Washington State, it doesn't really matter how old the building is, right? If I'm going to start disturbing a bunch of drywall, then the asbestos regs kick in. And the age of the building really has no play in that. So just understand that and understand what your local laws and regulations look like. Also use the appropriate personal protection equipment as soon as we start disturbing this stuff. Silica has become a much greater concern in recent as we've become more aware of silica dust and silicosis. So always wear your personal protection equipment as soon as you start disturbing assemblies. That and you just don't know what you're going to find, right? So have the personal protection equipment. All right, so that's a little bit on access. Now let's get down to the meat and potatoes of drying interstitial cavities and spaces. The biggest piece of drying an interstitial cavity in a space is first understanding where the wet surfaces are, right? I first need to establish, are there wet surfaces inside of this interstitial cavity? If those interstitial surfaces are wet, if they are affected, then I have options for ways to install my mechanical means to get air circulation into the space. Dehumidification will affect the interstitial cavity if I can install air movement that forces an exchange between the air in that cavity and where my dehumidifier exists. Whether I'm feeding the equipment directly with dehumidification, or I'm just forcing that air into the living space and then dehumidifying that with the rest of the air that's within that space. Understand as you install the system, is the air in that interstitial cavity air that I want to mix with the living space? We just talked about hazardous materials and concerns like that. If I'm concerned about the cleanliness of the air in the interstitial cavity or space, then we'll reverse that setup. Instead of forcing air into an interstitial cavity or space and out into the living space and then dehumidifying it with my dehumidifiers, we're going to do the opposite. We're going to pull the air out of that cavity in space. We're going to properly filter it or dump it outside. If we properly filter it, we can dehumidify with the interior. If dumping it outside is not practical, right? So just understand based on the cleanliness of that environment, which direction you want to run these systems we're about to talk about. We can put air in if we're not concerned about the cleanliness, which will be generally your most powerful drying approach. But if we're concerned about contaminants, we want to do the opposite, okay? So I'm going to talk about 4 different general categories of equipment here as we talk about drying interstitial spaces. They are the traditional centrifugal blower, right? This is just the carpet dryer, which can make a good inter-air drying system for a cavity or a void. It can in the right circumstance, and I'll talk about why. We have its cousin, the centrifugal blower HP. So these are the 1 horsepower variants. And there are a lot of different accessories, modifications, and kind of varieties of how this 1 horsepower blower can be modified into an inter-air drying system. We're not going to cover off on all those accessories, generally speaking. In fact, some of these 1 horsepower blowers come with those accessories permanently attached to the snout or the outlet of the air mover itself. Another category I'm going to talk about is something I'm going to call the bouncer blower, which sounds kind of odd for us to be talking about bouncers, those big castles you inflate, the kids jump around on at the fair. It sounds odd for me to throw that into this mix, but that's what for example, the Dry-Ease Airwolf is. It's a bouncer blower. And there's a reason why these make very good inter-air drying systems. You'll learn why here in just a second. And then last but not least, we're going to talk about the full-blown inter-air drying system, the dry force, if you will, the inject-to-dry of the world. And we'll talk about why those are truly inter-air drying systems and what makes them different. So first, let's talk about the centrifugal blower. As we get into these, 2 stats or specs that I'm going to talk about with each one of these. One is volume, the other is pressure, right? When it comes to air movement and how air helps dry a surface, there are 2 things that are important about that air movement. And this should sound familiar. One is how much air am I moving through the space relative to the size of the space? In other words, air exchange, right? How often am I replacing all of the air in that space with new, fresh air, that rate of circulation? And that's all about the volume of air, okay? The second before I get down to pressure, the second thing about that amount of air is also how quickly it moves across the wet surface. The nice thing about interstitial spaces, though, is that they're relatively small, right? And as long as I have a good rate of exchange through the space, then air is going to have some velocity across the surfaces. It doesn't take a lot of volume to create good movement, a good rate of movement through an interstitial cavity space, at least most of them, those that are relatively small, especially like a hardwood floor, for example. We're talking about very, very small spaces. So if I can get an air exchange through there once every minute, that air is actually moving pretty quickly underneath that floor. So I don't need a tremendous amount of volume to make that happen, but we need some, right? And generally speaking, the more volume I move through the space, the more rate of exchange and the better the velocity, right? So higher volume is definitely better, right? But sometimes in interstitial cavities and voids, that can be difficult. Because that's difficult, the second spec that I'm going to talk about with each one of these is pressure. Pressure is a generalization for, in this presentation, for how well the air mover overcomes resistance to airflow, right? If I were to give you a big giant straw from a 7-Eleven Slurpee, right? And you were to blow through that straw, it's a pretty big straw. You can blow through it pretty easily. There's not a lot of resistance. You don't have to create a lot of pressure in your lungs to make air move through the straw. But if we reduce that down to a coffee straw, right, you have to press a lot harder with your lungs and your diaphragm to get that same amount of air to move through that straw. That's the same with interstitial cavities and voids. The smaller the access and the tighter the space, the more pressure we need to force air to move through that environment or through that space. So pressure becomes a really critical element to these drying systems. The tighter the spaces, the more we lean on pressure. The more open the spaces, the more loose the spaces, the more we want to continue to rely on volume. Because remember, volume is what does the work, not the pressure. The only reason pressure becomes important is so that we can create the volume through the space, right? If there's resistance. So hold those in your mind. I know it was a long conversation to keep in your head, but keep that in your head while we go through each of these air movers. So first, let's talk about the centrifugal blower. The centrifugal blower it's a great air mover in general because it produces a really good volume of air, right? Generally speaking, the centrifugal blower is going to be somewhere in the neighborhood of about 1,000 to 1,400 cubic feet of air per minute, all right? It also produces, a fair amount of pressure down here in yellow. It's not great for pressure, but it's a fair amount. And that's the reason why traditionally we could use these for shoving underneath the corner of a carpet and floating the carpet. That's why you'll see these used a lot for, inflating things in the entertainment industry, just the different types of, large inflatables, like a big gorilla sitting next to a car lot, because they have a good amount of pressure, just not great. Because they do have some good pressure, they're blowers, not fans, and that blower wheel on the inside does create a good amount of pressure at a very high volume. These are actually great inter-air drying systems when we're talking about very loose and open spaces. And for ventilating very large and open spaces. And I'll talk about some examples of where we would apply that in just a moment. The cousin to that is the 1 horsepower centrifugal blower. So exactly the same on the outside. The only difference is when you go to pick it up, if you didn't know you were grabbing an HP, you might pull your arm out of your socket, right? Because it weighs 3 times more. It's got a much bigger motor in it. It's going to blow a lot harder with that much bigger motor, which is going to give you more CFM. These can easily approach 1,800 to 2,000 CFM. In fact, some are a little bit higher than that. But the kick is that they have a lot more pressure behind them. So I'm going to give you some analogies here by what I mean on pressure. A centrifugal blower, traditionally the way these are measured for pressure, a centrifugal blower is measured in inches of static pressure. All right, and I'm not going to get into the details of what we mean by inches of static pressure, but I'm going to give you some numbers so we can compare them. A centrifugal blower is about 1.5 inches of static pressure. The 1 horsepower variant is about 3 to 3.5 inches of static pressure. So without knowing what static pressure means explicitly, just understand that the 1 horsepower version is going to about double that. All right. So that gives me the option to then reduce the airflow down to 1.5, 2 inch, 3 inch ducting, right? And then deliver that air through that ducting through boots, through small holes that I would put into a toe kick or at the base of a wall cavity, right? It allows me to reduce the air even further into 1 inch tubes that I can run into wall cavities and still get a reasonable amount of flow. At 3 to 3.5 inches of static pressure, all of those are going to lose airflow from the air mover. All of them are going to create restriction, but you're still going to get a decent amount of flow for that wall cavity, that space, or that toe kick that you're going to hook it up to. So now let's move to the next one. Why the heck are we talking about bouncer blowers? So a bouncer blower it's a lot like a centrifugal blower, but the blower wheel, the scrolls on the blower wheel are much more elongated. So as it spins, it creates a lot more surface area to create that airflow. Not as much volume, but because of the surface area, a lot more pressure. So the volume kind of takes a hit. It drops down in volume a bit, but look at what happens to pressure. The pressure goes up substantially. Now we're talking about 7, 8 inches of static pressure. And just think about it just for the purpose of what it is. A bouncer blower, what it inflates, you can stand on, right? That's how much pressure is at about 7, 8 inches of static pressure. That's a lot of static pressure. And now at this point, we have enough static pressure that we can begin to force air through the little fluted assemblies underneath the hardwood floor. That's a really long coffee straw, right? And we're blowing really hard to get any air to move through that. And at about 7 inches of static pressure, that now becomes possible, right? Also very, very effective in drying wall cavities that are built with insulation. There's not a lot of electrical running through it. There's not a lot of opportunity for air to move from one cavity to the next. We need to put a lot of pressure behind it. These start to really shine when we get into those types of restrictions. And then last but not least, we have the true inter-air drying systems. True inter-air drying systems focus exclusively on the pressure. That's what they're engineered for, is the pressure, which means the volume takes a huge hit. But that doesn't really matter with a true inter-air drying system as long as I'm using it in the right places. Because a true inter-air drying system isn't made for drying cavities that are open and loose, where I need a lot of volume, right? Not large, open, loose cavities. If I were to hook an inter-air drying system up to, for example, I can think of a couple of different examples here, but a cabinet assembly where the toe kicks don't even really meet the floor or the base of the cabinet, and you have large open spaces underneath those cabinets, that's not the best use of that system because the cavity in there is relatively large, right? It's an open, loose cavity, and that would be much better served by one of the ones that we talked about up above, depending upon the hole size. And we'll touch on that. But the true inter-air drying system would be highly effective where we're talking about a tight wall cavity, where I don't want to make very large openings. I want to use a very, very small insertion point for my air that can be easily caulked over or covered with trim. And it's a very tight space. It's very difficult to get air to move through that space. The static pressure behind an inter-air drying system is going to start somewhere in the neighborhood of about 30 inches of static pressure, all the way up to about 60 inches of static pressure. Now, ponder that for a second. The bouncer blower had about 7 inches of static pressure, about 7 inches. Jump that up now to about 30, okay? If I could stand on something I inflated at 7, at 30, I'm going to inflate a wall cavity if the air can't move, right? Literally, if the air couldn't move from the wall cavity that I've inserted that pin into, if the air couldn't move to another cavity, then the cavity would literally start to inflate. That's not going to happen. The pin would back out first. But it gives you a sense for just how much power there is behind that airflow. It's a tremendous amount of force, which ensures that where I use the inner air drying system on these truly tight cavities, air is going to move. It will move from one location to another. So those are the different systems. Now that we understand kind of the difference in the specification on these different systems, let's talk a little bit about application. So where would I use each of these, right? I always like to distill this down to, so what does that mean and how do I apply it? So as an inter-air drying system, I would use the traditional carpet dryer, the traditional blower, on open unrestricted cavities such as the following. If I've got cabinetry with open toe kicks, all right, so I've got open space at the top of my toe kick, or the toe kick has been removed, so it's just a framing member that's back there, which is generally pretty loose, then that would be a great place for the use of this. Through a plenum, all right, through mechanical voids, and in the area above a drop ceiling. These are all very open interstitial spaces that don't have a lot of restriction. And they're great places to use something that has more volume, right? Why sacrifice the volume to get pressure when I don't need to? Because volume is what does the work. And that's kind of the lesson that I'm trying to really impart with this. Always start near the top of this list unless you need to move down this list. Because as you move down this list, you're getting rid of volume, right? Generally speaking, except for going to the HP, but you're losing volume, which means you're losing work, right? So if there's no restriction to the airflow, then stay with the air movers that produce the volume, because that's the end game, right? That's the end goal, is lots of air moving through that space. So open unrestricted spaces, stick with the blower that's going to give you the volume. If you start to see some restriction and you start to see some resistance, then the first step would be to move up to a 1 horsepower blower. And these would be some of the steel stud cavities you'd see in a commercial building, right? The 1 horsepower air mover is a great drying system if you can remove the vinyl cove, put some 1-inch holes behind the vinyl cove, and then use the boot system on these, which is just a vent system you can attach right up to the wall. You could put one of these boots off of this air mover. Actually, you could probably run 10 or 12 boots off of one air mover, but put that boot on 2 wall cavities, kind of centering over a steel stud, and then you could skip about 6 or 7 wall cavities, all right, and then put another boot down and create a massive amount of air exchange to that entire wall assembly, because the steel studs have knockouts in them, right? You're going to get a tremendous amount of flow through that entire space. Remember, we're talking about 2,000 cubic feet of air per minute, right? About 2,000 cubic feet per minute. Next down on the list would be the bouncer blower. You start seeing a little more resistance. I've got some uninsulated wood studded cavities, cabinetry where I just wanted to make a very small hole in the toe kick. But with a bouncer blower like this, you're going to need somewhere in the neighborhood of about at least a 1/2-inch opening, maybe slightly smaller, in order to get enough air through it. Hardwood that is over a sleeper assembly, so you've got some screeds or sleepers beneath it, so a larger air pocket on the bottom side. If you had to, you can use these also for a hardwood floor that's directly down on the underlay or deck. We'll talk more about hardwood floors in an upcoming episode. I had a lot of requests for that, so we will add it in. But the best system, if we're going to move truly to a hardwood floor, would be the one down below. So a bouncer blower, kind of in that moderate category. And finally, last but not least, a true inter-air drying system. When do I pull out the inject to dry, the dry force? When do I pull these systems out? So nail down hardwood floors directly on a substrate? Absolutely, okay? Because that's going to be one of the tightest restrictions that I'm going to deal with. Insulated, especially wood studded cavities, especially when I don't have electrical running through that particular wall cavity system. You're going to need that higher pressure. And then depending on the quality of the build and the install, in some cases also custom built-ins, right? If I've got custom built-in furniture in a space that's creating pockets behind and beneath those custom built-ins, very often those are extremely tight depending on the quality of the craftsmanship. And if that's the case, again, not only is the cavity tight, but the quality of the craftsmanship is going to be a bit higher. I'm going to be as least invasive as I possibly can. And the least invasive is going to be the highest pressure system because it also requires the smallest access hole. Okay, so that's kind of the categories of the inter-air drying systems that are present out there, kind of generalized into this list. And again, what I'm trying to impart with today's episode is, there are a number of options that we have for the type of inter-air drying system to use. And with this list, again, I would start near the top, right? Don't move down the list in inter-air drying systems unless the restriction or the tightness of the cavity dictates that you need to, or the quality of the surface and the size of the hole that you're going to make dictates that you move down the list. Those would be a couple of things I would use to justify moving down this list. Because at the top of the list, we're also talking about a difference in just the cost of the resource to deploy. At the top of the list, we're talking about the least expensive resource to deploy. At the bottom of the list, we're talking about the most expensive, both from the cost of the system and also the labor for the installation of the system itself. So use that as a priority as you're taking a look at this list. All right, so those are the different systems, some of the applications for the different systems. Let's move out of this now and talk a little bit about monitoring the systems. As I do this, I want to remind everybody about the Q&A. So before I get much further into this slide, if you have any questions on the content that we're covering today, go ahead and take the opportunity now to open up the Q&A, drop those questions in the Q&A, because I'm only a couple slides away from moving into the Q&A session, and I'll make sure that I hit those as soon as we finish the program here today. And don't have to restrict yourself to questions on what we covered today. Anything in the water damage mitigation world that's on your mind and you'd like to throw my way to see if I maybe have some insight for, don't hesitate to throw that in the Q&A. In fact, I love to be caught with surprise questions as long as they have something to do with water damage mitigation, right? Something to do with the industry. So feel free to drop anything in there. With that, let's go ahead and close out the conversation now. So how do we monitor an inter-air drying system? How do we know that an inter-air drying system is effective? And in simple terms, we monitor an inter-air drying system the same way that we do a dehumidifier, just in reverse, in opposite. We monitor a dehumidifier by measuring the air going into a dehumidifier, determining the grains per pound or humidity ratio. Then we monitor the air coming out of a dehumidifier in grains per pound or humidity ratio. The difference between those two tells us how much water the dehumidifier has removed, right? Grain depression. With an inter-air drying system, we're doing the opposite. We're measuring the same two things, how much air is coming from my inter-air drying system and how much air is going into the cavity to replace it, or the opposite, how much moisture is in the air I'm pushing into the cavity, so what's the source air going in, and then what's the temperature and humidity exiting the cavity or in the cavity, right? What's the difference between those two? The difference between those two, if you want to call it a grain depression, is how effective your inter-air drying system is. Now, if you take that information, you can do the same thing with it that we learned to do last month with dehumidifiers. Grain difference between what you're putting into a cavity and what's coming back out, that grain difference times the CFM of the system you're using to circulate it, divided by 71 equals pints, right? So if I want to know how well my dry force, is drying a hardwood floor, for example, right? Then I would measure the air in the room above the hardwood floor. How many grains do I have? Let's say it's 70. Then I would monitor the air being ejected by my dry force because it's pulling air up from underneath the hardwood floor. And let's say we have 90. If the room is at 70 and the air coming out of my dry force is 90, then what's happening on the way through? What's happening is that air is picking up 20 grains of water per pound. Per pound is every 14 cubic feet, right? And we learned last month to simplify that math and use what's on the screen here. Grain depression, that difference, 20, times the CFM of the machine, right, divided by 71 equals pints. And what you'll find is that a dry force that is getting you about a 20 grain difference on the way through is removing somewhere in the neighborhood of about 15 or 16 pints of water from the floor a day, right? That's a great documentation tool, great documentation tool. And it can be applied anywhere that we're using these inter-air drying systems. I just need to know the difference between the air that I'm placing into the space versus the air that's either in or leaving the space, and know the CFM at which we're creating that circulation. So it's a great way to monitor the effectiveness of the inter-air drying system itself, and also to justify its use, right? To justify the use of that particular system. All right, so with that, let's go ahead and do a quick wrap up and review here. And then after I finish the review, we'll jump into the Q&A session. So hold on with me here as I go through the quick review. Number one in the review, remember to consider full migration when you're looking at a water damaged space, right? It's not just what you can see that we're trying to dry. It's everything that has become wet and affected within that environment that we have to monitor, that we have to dry, we have to validate has achieved its drying goals. That means we need to think about assemblies as their full list of components and all the cavities that they create in between. That means my drying chamber isn't just what I see. My drying chamber is also the cavity in the wall behind me, potentially, if water has made it into that space. That needs to be part of my drying chamber. And so another good way to think about it is, where is the edge of your drying chamber? Is the edge of your drying chamber this wall surface, or is the edge of your drying chamber the other end of that assembly, right? The back surface of the next room, right? Is that the edge of my chamber? And the edge of your chamber needs to include the totality of that migration, right? Remember that 11 to 42% of the space that you're dealing with is interstitial, right? So how much time, energy, and resources are you deploying for what you can see, right? And how does that match up with the resources you're deploying for what you can't see, right? If 11 to 42% of what you're dealing with is interstitial, I would argue that 11 to 42% of your resources are probably needing to be dealing with interstitial, right? All right, so just think about it that way for a second. Hopefully that has a little impact on the paradigm. Pressure versus volume. Remember, volume is what does the work with an air mover. How much air is it moving? Technically, it's velocity, but volume is what does the work for an air mover. So don't sacrifice volume if you don't need to. A lot of people automatically think it's a cavity. I need a dry force. Not necessarily, right? How open is that cavity? How loose is that cavity? How easy is it for me to create circulation for that cavity? If the resistance isn't high, I don't need high pressure, right? I need good volume and the accessories to put it there, right? If the resistance is high, that's when I've got to go for the bigger guns, right? And that's when I've got to go for the bigger pressure, okay? And then monitor for that quote unquote grain depression, right? That's how we understand the effectiveness of our interstitial drying systems or inner air drying systems in those cavities. Monitor for that grain quote unquote depression, okay? All right, so that wraps us up for episode number 7. Just a quick close up here before we hit Q&A. Again, my name is Brandon Burton with CoreLogic, and I will be holding these sessions monthly. Next month, when we come back, we are going to hit number 8, episode number 8. And that's going to be psycho for the psychrometric chart, right? It's my opportunity to really geek out on the psych chart. My favorite thing to talk about in this industry is psychrometrics. For anybody who knows me, you know that well. So August 23rd at 10 a.m. Pacific, 12 Central. If you really want to brush up on your psychrometry, we're going to dive super deep into the world of psychrometry. I promise you, even if psychrometry is something you're using on a daily basis, you're going to walk away from that conversation with new tools and new resources on how to apply psychrometry. And if psychrometry is brand new to you, I'm going to promise you I won't bury you with technical speak. All right, you'll walk away understanding psychrometry. All right, so especially for those of you attending today, if you've got some folks in your business that you'd really like to get familiar with psychrometry that aren't today, get them on that episode. And it's my favorite thing to teach, to talk about, to preach about, if you will, is psychrometrics. So I guarantee they're really going to enjoy that episode. And the final note I want to make there is don't hesitate to extend that invitation beyond just your organization. If you've got some folks that you work with that need to understand psychrometry and the role of psychrometry in drying, this would be a great session to kind of invite them in for, to have them go through that, because we're going to start with the basics and understand what psychrometry is. Then we're going to launch right from there into some of the more advanced, which really drives home how important psychrometry is to mitigation. So I'm excited about that episode. If you can't tell, we'll be super excited to see all of you there.